Okay, so you should now see my screen. Is that okay?
Yeah.
Yeah, okay, thank you. So yeah, so what I'm going to talk about is work that has been done earlier this year during the thematic semester at Fields, and it's joint work with Patrick and Jean-Philippe. Let me stress that it's work in progress. Some of what I'm going to present is very recent, and there are still indeed open questions that we'd like to answer in this project. So, so throughout this talk, we'll be living in o-minimal expansions of the real field, expansion by functions, by a collection of functions, and we'll denote by def the collection of definable sets of such a minimal expansion of the reals. We stay in the reals, we never get out of the reals. And for the purpose of this talk, I will say that the function f, the real function f, is o-minimal if the expansion of the real field by f is o-minimal. And if I have another function g, I will say that g is definable from f to mean that the graph of g is definable in the expansion of R by f. Okay, so the kind of problems we're going to look at are the following. We are given two o-minimal functions, and we suspect that one is not definable from the other. We're asked to prove it. For this kind of problem, historically and empirically, there seems to be a dichotomy depending on whether f and g are definable in R and X or not. So within R and X, usually what happens is that we know the function so well that we know of some algebraic independence properties. I'm thinking of axis theorem and variation on that, which are useful to establish non-interdefinability. And from the point of view of model theory, of the model theoretic tools, usually what happens is that what is used is that we know that the structure Rf is model complete. This gives us information about the definable functions at generic points. And usually knowing the definable functions at generic points is enough to prove this kind of results. Well, when we're outside R and X, we don't usually know enough about the functions in terms of transcendence, and maybe even not enough in terms of functional equations. So what is usually useful in this case is more analysis, as Alex mentioned, and especially asymptotic analysis. And in terms of the model theoretic tools, model completeness is not usually enough. We need a strong form of quantifier elimination because we do need information about definable functions also at singular points, and model completeness does not provide this. So today, my talk is going to be about the second scenario. So there will be asymptotic analysis, and there will be a strong form of quantifier elimination. A remark, again, historically and empirically, if you have a function which is not definable in R and X, but which is suspected to be o-minimal, it is usually very difficult to prove directly that the expansion of the real field by it is o-minimal. So what usually happens is that one constructs a suitable large o-minimal expansion MF of the reals, or even of R and X, in which F is definable. And large here means stable under some form of resolution of singularities, which is what usually leads by a standard method by Gabrielov to model completeness, which reduces the complexity of the problem of o-minimality, since we only need to worry about the number of connected components of existentially definable sets. Okay, so accordingly, the non-interdefinability problems we will consider here will be restated in a following way. So suppose we have f and g o-minimal and not definable in R and X. So they're o-minimal, and this is witnessed by some large mf and mg respectively. And the discussion we're going to have is not whether f is definable from g, but whether f is definable from mg. It's the strongest statement, and vice versa for g and f. So the motivation for this kind of question, well, one of the motivations for this kind of question is the following. So suppose that you have such f and g and that you've proven that they're not interdefinable. Then there's a new question that arises naturally, the question of compatibility. That is there a minimal, even larger minimal structure in which they're both definable? So we know that there are examples of o-minimal structures which are not compatible. So this is not a trivial question. So in this talk, I will start by the beginning of this talk. I will start by concentrating on an example of two specific functions. So the Euler gamma function at plus infinity and the Riemann zeta function at plus infinity. And there will be questions about interdefinability. So you may ask why at looking at plus infinity. Well, gamma and zeta extend meromorphically to the whole real line, but with an infinite discrete set of respectively poles and zeros on the negative half line. So their extension to the whole of R is certainly not o-minimal, and the restriction to any bounded interval which avoids the poles is definable in Rn. So the only question left in terms of minimality, the only interesting question left is what happens at plus infinity for either of them. So back at the end of last century, Lau, Angus, and Dave proved that both of these functions are not definable in R and X, but it was suspected that it would be o-minimal. And this was proven by Lau and Patrick a few years later. So zeta, I won't say it anymore, it's zeta at plus infinity, gamma at plus infinity. I will talk about zeta and gamma. So zeta is definable in an o-minimal structure, which is called R sub n star x. And gamma is definable in a minimal structure called RGX. So I will describe R n star x later, and very probably Patrick will talk about RGX, so I won't say anything about this one. So the question that is left is, are they interdefinable? And this is one of the things that I will address here. I will prove that no, they're not, which opens the way to the question of compatibility, which would be the topic of Patrick's talk immediately after mine. So the question of interdefinability, or rather non-interdefinability, half of the question was already answered 20 years ago by Lau and Patrick, who proved that zeta is not definable in the structure that witnesses the minimality of gamma. And 20 years later, with Jean-Philippe and Patrick, we proved, we settled the question, we proved the other half of the question. Gamma is not definable in the structure that was used to prove that zeta is a minimum. So let me say a few words about the proof ideas. So we give an explicit description of the Hardy field of the structure R n star X as a subfield of the field of trans series. And this provides a kind of convergent transasymptotic expansions for germs definable in R n star X. Then why is this useful? Well, it is well known that there is a function here in blue, which is linked definably to gamma, which has a divergent Taylor expansion at 0. Hence, this function cannot be definable in R and star X, and neither can gamma. Now, let me say first a few words to those of you who are familiar with the proofs of the results in pink from 20 years ago. And then I'll talk to the rest of the audience. So for those who are familiar with this kind of results, although the end argument, the divergence of the Taylor expansion of this function has been used before, namely to prove that gamma is not definable in R and X. Here we use, for the rest, we use a different approach. Different in the sense that we really want to describe explicitly the trans series that occur as asymptotic expansions of germs definable here. So we'll see, I will say a little bit, no, I will say a lot more about this in the next few slides. And I should say, so this explicit description is inspired of work which is much more recent, so from 2019 by Kaiser and Speissegger, who gave an explicit description of the Hardy field of R and X. Okay, now for the rest of the audience, if you're not familiar with at all with this kind of results and with the words that are mentioned here in the proof, now I will define them. So in particular, I will define this structure and I will say a few words about trans series. Okay, so we need to construct a certain number of formal objects. So we'll start with a generalized power series in one variable x. So these are simply power series where the monomials have real non-negative exponents. And to make it into a ring, we need a hypothesis on the support. The hypothesis is that the support is well ordered. And we can play this game in several variables in the obvious way. So now x bar to the r bar is x1 to the r1 times xn to the rn. And the hypothesis on the support is just component-wise. Okay, among these generalized power series in several variables, there's a subclass of generalized power series which are convergent. In the following sense, there exists a Pauli radius such that the family of monomial terms a, r, x to the r as a family of functions is summable and even uniformly summable on the polydisk of radius rho. This class, the class of convergent generalized power series, was introduced and then used by Lau and Patrick to construct the structure R and star from the collection of all convergent generalized power series, exactly in the same way that you construct R sub n from the collection of convergent normal power series. And also they proved that the structure is a minimal. Notice that zeta of minus log x is such a convergent, is one of these convergent generalized power series, which proves that zeta itself at plus infinity is definable in the structure R and star, to which we add x. And by a general result, this is o-minimal. Okay. Now let's go back to the ring of generalized power series in one variable as a formal object. And let's look at the fraction field of it. So this is the field, can be described as the field of generalized Puiseux series in some sense. So you just need to multiply by a power.
Can I ask a question?
Yeah, sure.
The summability there, that's just via finite sums.
Yeah. So it's
ordinary finite sums.
The supremum of all.
All the finite. Okay.
Yeah. And it's, I mean, with absolute values, it's an absolute sum.
Absolutely converged.
Okay, so let's look at the fraction field of R of X star, which I can describe this way as Puiseux series, but let me also describe it a different way. So we can also, thanks to the hypothesis on the support, write these objects as sums over some ordinal of terms of the form C alpha X R to the alpha, where the C alpha are the real coefficients, and the R alpha are an increasing sequence of real exponents. Now this way of seeing things is when the variable X is infinitesimal, and we're going to do asymptotic extensions at infinity. We're going to work with the Hardy field. So let me go at infinity and change variables. So y will be x to the minus 1. And let me just rewrite this in terms of y. So this is the collection of all sums indexed by some ordinal of terms of the form C alpha, y to the S alpha, where now the exponents form a decreasing sequence. So this object is usually called the Hahn field with coefficients in R and monomials, real powers of y. Okay, and the next step will be to, I mentioned trans series, so I need to go there. So I want to talk about the field T, also denoted historically this way, the field of a logarithmic exponential series introduced in the 90s by Van den Dries, McNair, Marker, and studied extensively in a recent year by Aschenbrenner, Van den Dries, and Van der Hoeven, and whose model theory is now well understood. I don't know if I couldn't attend yesterday's talk, so I don't know if this has been already introduced formally. I will assume, so these are the traditional trans series of bounded logarithmic and exponential depth. I will assume that all of you have at least a vague idea of what a trans series is. So it's a formal series whose monomials involve powers of the variable, exponentials, and logarithms. And I will recall the properties that I need along the way. So one thing that you need to know is that there exists a multiplicative abelian ordered group called GLE, such that the field of trans series can be seen as a proper subfield of the Hahn field with coefficients in R and monomials in GLE. So this means in particular that every trans series can be written as a sum indexed by some ordinal of terms of the form C alpha G alpha, where the C alpha are the real coefficients, and the G alpha are the monomials, so they are transmonomials, they're in GLE, and they form a decreasing sequence. So as you understand, since we're going to talk about asymptotic expansions, we'll need to talk about the leading term and the leading the leading monomial, the leading coefficient, and the leading term of such an asymptotic or even trans-asymptotic expansion. So this is why we will need this kind of way of looking at trans series. Okay, so there was a theorem 1. This suggests that there is also a theorem 2, and theorem 1 is actually a consequence of theorem 2. Although theorem 2 chronologically came afterwards. So I'm going to state, I'm going to give a first statement, which is a little bit imprecise, because I want to avoid technicalities in the first statement. And then I will clarify during the rest of the talk. So we work with a structure R sub A. So you should think of R sub A as any of the known model complete polynomially bounded o-minimal expansion of R sub n, expansion by a collection of functions A, and which has infinity cell decomposition. Okay, to make it short and even more imprecise, think of any known polynomially bounded o-minimal expansion of the reals, and then set aside the only one that does not have a infinity cell decomposition. Well, if you don't know any, here are some examples. So R and star that I just defined, RG that and RG star that Patrick is going to talk about, generated respectively by multi-summable series and generalized multi-summable series. Any structure generated by a quasi-analytic Danjois-Kalman class, or the structure that contains the structure for the moment that contains some Dulac maps in the hyperbolic non-resonant case. I'm certainly forgetting some. Okay, then what? Then we construct a truncation closed ordered field embedding phi of the Hardy field of the structure RAX, so the expansion of RA by the full exponential function, into the field of trans series, which defines an explicit transasymptotic expansion. So let me first define transasymptotic expansion and then maybe say what I mean by explicit. So take a germ in the Hardy field of the structure. I just said that there is an embedding, so take its image, it's a trans series, write it as a Han series. Then the transmonomials that are used in this trans series are also in an image of this embedding, hence they come from germs, which I call M alpha. And F is asymptotic to the per-image of the first term of the trans series, and of course this I can repeat omega many times, but I can also go further, hence trans asymptotic expansion. For every ordinal beta, there exists a germ F beta, which is mapped to the truncation at beta of the trans series phi of F, and which hence allows me to subtract F beta from F, and what I get is, again, the first term of an asymptotic expansion, and I start again. Okay, so notice that, maybe you don't know that, then, well, know that the transmonomial G alpha are not in general functions. It's not e to the x, not necessarily. And the series, the sums here are not necessarily convergent. However, the description is explicit enough so that we can learn something about the transasymptotic expansions of the germs definable in RAX, and we can use this in non-definability results. This is the general philosophy of the fact. Okay, so let me say once more, this theorem concerns all known model complete polynomially bounded o-minimal expansions of R and with infinity cell decomposition, i.e. The examples I gave below, to which we add the exponential function. So the question is now to go towards a more precise statement. What do all the structure have in common? So this is what I'm going to talk about now. What they have in common is that, well, first of all, they all have the form a polynomially bounded structure generated by a collection of function A, to which we add the exponential function. Not all minimal structures have this form. And moreover, the collection, well, one can choose, one can generate them with a generate the polynomially bounded part with a collection of function A, of restricted functions on cubes, which have the following properties. Well, A is stable under a certain number of both geometric and formal operations, which allow resolution of singularities, essentially. I call them generalized blow-ups. And more importantly, A is generalized quasi-analytic. This means that there exists an injective algebra morphism, which to the germ at zero of a function in a collection A associates injectively a formal generalized power series. And this association, this morphism, is compatible with the generalized blow-ups, commutes with them. Then for such structures, a theorem of Jean-Philippe and myself from 2015 says that the structure generated by A is model complete, o-minimal, and polynomially bounded. And a theorem of Lau and Patrick's from 2000 says that if RA is any polynomially bounded structure such that restrictive exponentiation is definable in it, so in particular any of the above, if you add the full exponential, then it stays o-minimal. So as I said, model completeness, o-minimal and model complete. Model completeness is not enough for what we want to do. So I will need to extract more information from both of these theorems. So what I need is the following. For the polynomially bounded part, we also know that every germ definable in RA can be expressed as a term of the following language, the language of ordered rings, and then I put as a function symbol for every function in the quasi-analytic algebra A. And I need something a little bit more. I need to add also all the definable powers, a symbol for every definable power. And regarding adding exponentiation, if we add x and log to the language, then the expansion, the exponential expansion, has universal axiomatization and quantifier elimination over the polynomially bounded one. So as a consequence of this, we get what I call strong quantifier elimination. So let A be a generalized quasi-analytic class as defined in the previous slide. Then every germ of a definable function in Rax can be expressed as a term of the language LAX, which is the language of ordered rings. And then, of course, I need to put a function symbol for every function in a quasi-analytic algebra A. And then I just add x and log. Okay, so let me just say briefly a few words about the ingredients of the proof of this corollary and the results in the previous slide. So there is one non-constructive ingredient, which is an o-minimal polynomially bounded preparation theorem due to Lau and Patrick, inspired of the Rolin subanalytic preparation theorem, but which, unlike the subanalytic one, doesn't have a purely geometric proof. And the rest of the ingredients are purely geometric. So it's resolution of singularities for generalized quasi-analytic classes, and the logarithmic and the exponential version of the preparation theorems, which are constructed over the polynomially bounded one. Okay, so why do I insist on what's constructive and what's not? Well, first of all, this is somehow relevant to what I do in general. Well, it is also, I mean, it, as we'll hear on Friday in Gal's talk, effective methods in o-minimality are getting more and more relevant to applications. And also you should know that many of the geometric techniques used here make sense even if you're dealing with a structure that you don't know that it is o-minimal. And you might want to use them to prove o-minimality. So having an o-minimal black box is no use for this kind of thing, which is why we would very much like to give geometric proof of this result. Okay, it will be the only non-constructive ingredient in today's talk. Okay, back to the corollary and what this means for us. Let me call TAX the collection of all LAX terms in at most one variable. So a consequence of the corollary is that the map that to every such term associates the germ at infinity of the interpretation of the term in R, so which is an element of the Hardy field, is surjective. So I have a surjective map from terms to the Hardy field. So the next thing I want to do is to define the map from terms to trans series. In order to do that, let me equip the field of trans series of an LAX structure. So I'm sure all of you know how to make T into an ordered exponential field, so I will not comment on that. Let me just tell you how I will interpret the symbols, the function symbols relative to the functions in a quasi-analytic algebra, generating algebra. So define the interpretation of such a symbol applied to an n-tuple of trans series in the following way. If the trans series are all infinitesimal, then take the image of phi under the quasi-analyticity morphism. So this is a generalized power series in n variables, and compose it with the trans series sigma I. This is a well-known construction. I guess it's Neumann's lemma that assures you that this makes sense. And you get a trans series. If one of these sigma I is not infinitesimal, then set this interpretation to 0. Okay, then I say that this way of seeing things allows me to define a map, which I'll still call hat, from terms to trans series. So given a term T, the trans series T hat is the interpretation of the term T in the field of trans series, in the sense that I've just defined, evaluated at the transserial variable y. So the situation is the following. We have a surjective map from terms to germs, and a definitely not surjective map from terms to trans series. And we would like to somehow complete this diagram by an embedding. Now I can tell you it will be an embedding also in the sense of the language LAX of the Hardy field of RAX into the trans series, which moreover has the property of transasymptotic expansion. So let's forget for a moment about the transasymptotic expansion. Let's focus on the asymptotic expansion. So this is the property we're looking for. We want the germ to be asymptotic to the preimage of the leading term of the trans series associated to it. Let me show you an example that this is not so trivial. It's not so clear how to define such a map phi. So take a germ and suppose that it is represented by this term. So this is definitely a term. It's a composition of x again, and then this phi is in a quasi-analytic algebra, and then there's log of some of the things, and there's a psi which is also in a quasi-analytic algebra, and the phi and the psi are applied to transmonomials. Well, so what does it mean? I can hear my voice. Okay. What does it mean that phi and psi are in the quasi-analytic algebra? Well, it means in particular that their hat, the quasi-analytic hat, are generalized, possibly divergent power series, generalized power series. You notice that I applied them to infinitesimal monomials. And now, just by looking at this expression, well, first, okay, so this is a term, and I want to, so I can, by hat, I can associate a trans series to it, as I defined in the previous slide. But the trans series, in a way, I need to write the trans series in a way that I can read off its leading term. So let me write this trans series as a Hahn series. Now, by looking at the term, it's not so clear how to recover the leading monomial. Who is the leading monomial of this expression? It's not so clear. And even if it were clear, it's not clear that such a transmonomial comes from a germ or from a term. Why should it be the case? And thirdly, even if that were the case, it's not at all clear that the fact that this is the leading term of the trans series should imply that the germ is asymptotic to the germ corresponding to it. Okay, so what we're going to do is to define a section of this map, tilde, which picks a term representing a germ of a special form from which the leading term is easily readable. This is what we're going to do. So to get inspiration on what should be the special form of the term, we will use the following fact, which is a consequence of the axioms of quasi-analytic classes, but of generalized quasi-analytic classes, but not a trivial consequence. It does need some resolution of singularities. And the fact is the following: if you take a germ in the quasi-analytic algebra, then the germ tends to 1 if and only if the constant term of the generalized power series associated to it by the quasi-analyticity morphism is 1. In other words, the germ U is bounded and bounded away from 0 if and only if the series U hat is a unit. So this suggests to give the following definition. Let T be a term. Let me say that T is a monomial if the trans series associated to it is a transmonomial. And let me say that T is a monomialized if T has the following form. It has a form M0 times U of M1 up to Mn, where the Mi's are monomials and the M1 up to Mn are infinitesimal. And U is a function symbol which comes from a germ of the quasi-analytic class, which is a unit. Okay. Then, thanks to the fact in green, it is easy to see that if you have a term which is amonomialized, then if you map it to its trans series, you get what you want, at least for the beginning of the asymptotic expansion. In other words, the germ associated to it is asymptotic to C0 times the germ of M0. And on the side of trans series, the leading term is exactly C0 M0 hat. So, okay, so what is left? I guess I only have 8 minutes. What is left to do, there's a lot still that we have to do. We need to prove that every germ in the Hardy field can be represented by an A monomialized term. And then we need to deal with trans-asymptotic expansions. So this is what is actually done in the proof. I don't know how much I can tell you about this. So let me choose. Yeah, okay. Let me go through this slide. So in order to do the rest, what was in red, I guess I need 2 more definitions. So let A be a generalized quasi-analytic class. I will say that A is truncation closed if the following thing happens: if phi is a germ in a generating algebra, and we write the series corresponding to it as a series in the last variable with coefficient in the previous variables, then if we truncate it somewhere, then the truncation is still in the image of the morphism. And I will say that A is natural if, to say just very briefly, there is no accumulation in the support. These are objects, these are functions to which we associate generalized power series. In generalized power series, exponents are allowed to accumulate. We want to concentrate on classes in which this phenomenon doesn't happen. Okay, then the key lemma for what is left to do is a splitting lemma. And it applies on the one hand to the structure R n star X, so to the case A equals n star, and on the other hand to any generalized quasi-analytic class which is natural and truncation closed. So this still covers all the known examples. So what does the splitting lemma say? It says the following thing: if you take a term which is A monomialized and M is any monomial term, and you write the trans series associated to T as a Hahn series, then there is a term whose trans series is the truncation at the monomial M hat of the trans series of T. So once we have this, let me just tell you why this is the key lemma. Well, for one, I'm sure you can see that if we want to do trans-asymptotic expansion, we need to be able to truncate. But even for the non-trans-asymptotic, even for the beginning of the expansion, for the construction of the embedding, we actually need this lemma, and I'll try to explain why. So one of the things we need to prove is that every term is monomializable. Every germ is representable by a term which is A monomialized. So this is proven by induction on the complexity of the term. So suppose we have already proven it for T, and we want to prove it for the exponential of T. So those of you who are familiar with trans series know that what one needs to do is to split T into its purely infinite part, its constant term, and its infinitesimal part, and then keep the exponential of the purely infinite part as a monomial and expand as a Taylor series the exponential of the infinitesimal part. So this, by the inductive hypothesis on T, gives us immediately that x of T is monomialized. So this is a monomial, and all the rest is an A unit. So the splitting is crucial. Okay, I had prepared examples of splitting, which I don't have time to go through, but let me just tell you one thing. This splitting thing, even in truncation closed quasi-analytic classes, is non-trivial. It's not a trivial consequence of the fact that A is truncation closed. This is because, well, truncation is a very special kind of subseries. And in general, quasi-analytic classes are not closed undertaking subseries. If you take a subseries of a series that is an image of the quasi-analyticity morphism, there's no reason why the subseries should also be an image. It is, on the other hand, trivial for the structure R and star X because everything is convergent there. So a subfamily of a summable family is still summable. But in all the other cases, it's not trivial. Okay, so I will skip the examples and unfortunately also the explicit construction of the Hardy field as a subfield of the field of trans series, and I will go back to the applications at the beginning of the talk. So the applications to non-definability of this kind of result. You're given a collection A, a quasi-analytic algebra A, and a function, a real function f, and you want to prove that f is not definable in Rax. So the general philosophy is that by theorem 2, you're able to describe quite explicitly the properties of the Hardy field seen as a subfield of the field of trans series. In other words, you're able to describe the transserial properties, the properties as trans series of the transasymptotic expansions of the germs in H. So, for example, properties of the coefficients, property of the support, convergence, non-convergence, summability, this kind of things. And then all you have to do is to prove that the transasymptotic expansion of F does not have one of these properties. And this is enough to prove that F is not definable in the structure. So as an example of this, which is not too technical, take a generalized, well, take a quasi-analytic class, which is not generalized, which is classical. This means that the image of the quasi-analyticity morphism contains only a standard power series. Then zeta is not definable in it. And this is because it is easy to see when you construct the transserial field associated to such a structure that every element of it is grid-based. So this means in a specific case of generalized power series, this means that the support is contained in a finitely generated lattice over N. Now, zeta of log y is coincides with its transasymptotic expansion, and its transasymptotic expansion does not have this property. Hence, zeta cannot be definable in such constructions. Okay, so I'll skip the question and I'll go directly to the conjecture. So I'm hoping that this kind of methods will be useful to prove the following conjecture, which I'm sure you all agree with. O-minimalists haven't accidentally solved Hilbert-16 problem yet. In the following sense, this is an exercise. For every known o-minimal expansion of the reals, find a Dulac map which is not definable in it. So this is easy for some of the examples. It's less easy for other examples, and I'm hoping that these methods can provide this kind of result. Thank you very much.